So welcome everyone. It's at the Conversations at the Royal. So this is an ongoing seminar series where we do an outreach for the public as well, so that you know what kind of work we're engaged in and what's new and exciting going on. So today is going to be particularly exciting, as you will see. I'm really thrilled to see so many of you here. I mean, I was worried about it being so beautiful outside that I thought you might be wanting to spend more time there than in here, but so it tells me how dedicated you are, and hopefully you'll be rewarded for that. But for those that don't know me, I'm Zulmar Ali. I'm the president and CEO of the Royals Institute of Mental Health Research. And we are very interested in tonight's talk because we have recently invested in a brain imaging center, which is one of the very few around that's dedicated to neuroscience and mental health. So you'll hear a lot about why this technology is so critically important to our furthering diagnosis and treatment for mental illness. So it's an absolute pleasure for me to introduce you to today's speaker, who comes to us from Cornell. Dr. Connor Liston was a top choice for our young researchers who are actually having a full day tomorrow. They organize a conference for the young people, by the young people, and their keynote speaker is going to be the same, Dr. Connor Liston. So he's doing double duty, so he'll do tonight and then he'll do tomorrow's talk. Different topics. So currently, Dr. Connor Liston is a professor of neuroscience of the Brain and Mind Research Institute at Cornell. And in terms of his education, he did his undergraduate at Harvard and then went on to earn his doctorate degree from Rockefeller University, and then finally completed his medical training at Cornell. Then he went for a bit to Stanford and then back at Cornell. So that's where he's hanging out right now. And his work is very interesting. His lab is primarily focused on understanding the underpinnings of mental illness. So his work focuses on understanding how the cells in the brain communicate with one another, what the circuits in the brain look like in normal circumstances versus what happens to the circuits in mental illnesses. Because mental illness is not a thing that you can see an abnormality in the brain, but rather an abnormality in the brain functioning and how these circuits are operating. It's not a physically obvious sight. You cannot take a picture like an X-ray of the brain and see something broken, but you need to study it in much more intricate way to say how the circuits are working or not working, and that's what we're going to learn about today. And he's not only interested in understanding those circuits, but also underpinnings of how those circuits work. In other words, how do the neurotransmitters and neurochemicals make those circuits operate? And more importantly, then he's interested in the networks of how these circuits connect with each other to be involved in things like cognition and mental health. And so that's what you're going to hear about today. He's a very prolific individual. He's written scientific papers that have been published in some of the top journals like Nature, and he's been getting a lot of support for his work from National Institute of Mental Health, NIMH, in a lot of foundations, in Dana Foundation, and he was also a NARSAD Young Investigator, got an award for this. As I said, his research is published in some of the top journals, including Nature, Nature Medicine, Science, PNAS. Those are, for those that are in science, those are journals that are really top of the list. Dr. Liston investigates, as I said, how the various cells and the circuits work as a system in the brain, and understanding how various neurotransmitters modulate those functioning. And in addition to focusing on the brain cells, as I said, he's interested in processes at systemic level, so he's interested in rhythmicity in altered chronobiology in terms of sleep functioning and disruption of sleep, and particularly interested in young individuals because that's where there is a lot of neuroplasticity and the circuits are kind of much more amenable to change. So that's what is some of his areas of work. And his ultimate goal is to understand how the circuits in the brain get disrupted to give rise to mental illnesses. So that's the excitement, and that's why we're particularly happy to listen to talk. So without further ado, I'd like to invite Dr. Conor Liston as a special guest at this evening of Conversations at the Royal. And his topic is going to be finding and fixing broken brain circuits in novel subtypes of depression. So without further ado, Dr. Liston.
All right. Thank you, Dr. Murali, for inviting me here today. I'm really thrilled to have this opportunity to come meet everyone here today. I'm going to tell you about the initial results of efforts underway in my lab and in others to rethink the way we go about diagnosing mental illness and hopefully develop new approaches that can be used to inform the treatments that we select for our patients, and that's a big challenge. These statistics will probably be familiar to a lot of people in this room, but to some, I think they're surprising. They show you that psychiatric disorders now account for 5 of the top 10 leading causes of disability in developed countries. And by one measure, depression is actually the leading cause of disability. So it's a tremendously disabling illness, and it's a tremendously costly illness. We spend, and this is in 2010 dollars, nearly a decade ago, so I'm surely higher now, $210 billion by one estimate on depression, on treating depression, on lost productivity at work due to depression, and on treating other medical illnesses that are worsened due to depression. And I think it's not controversial to say, and this will probably ring true with many people's personal experiences here, that part of the obstacle to improving on these numbers relates to how we diagnose depression in particular and mental illnesses in general. So if we just pause for a moment to think about it, this is from our Diagnostic and Statistical Manual, the kind of textbook for making mental illness diagnoses. And it says that in order for a person who comes into my office to meet criteria for a diagnosis of depression, they need to have 5 or more of these 9 things. And that means, just doing some simple math, that there are at least 256 unique ways that someone can come into my office and still meet criteria for this depression diagnosis. And some of these are very different from one another. In fact, some of the criteria contain opposites of themselves, right? Weight loss or weight gain, insomnia or hypersomnia, sleeping too much. And so I remember learning this as a resident and kind of being, even a medical student, puzzled by the fact that somebody who has a lot of anxiety, physically agitated, can't sit still, sleeping 4 hours a night because they can't fall asleep, very anxious, lost a lot of weight, lost 30 pounds, no appetite. This person gets the exact same diagnosis as somebody who has no problems with anxiety. It's just profoundly low energy, not enjoying any of the things they used to like in life previously, sleeping 20 hours a day, can't get out of bed, gained 30 pounds because they have intense carbohydrate craving. These people seem almost like opposites of one another in many respects, and yet they get the same diagnosis, and oftentimes they get the same treatment. And so in a way, it's surprising that our treatments work as well as they do, perhaps. These two people probably don't have the same biological problem. And so just to give you kind of the message, the take-home message up front, what I want to convince you of today is that there's something to be gained by rethinking the way we diagnose depression, that coming up with subtypes of depression that have a stronger correspondence to biology and might help inform decisions, match treatments to the individual patients most likely to benefit from them, that approach could be really useful going forward. And that's really what I'm going to try to present some data to convince you of. Now, we're not the first to try this, of course. This area of research has a long history, and we've learned a lot from these efforts. And typically the way we've gone about thinking about subtyping in depression is to ask whether there are particular sets of symptoms that tend to co-occur in subgroups of people, and then try to draw circles around those subgroups of people and come up with labels, and then ask whether those potential subtypes can be associated with particular biological markers, hormones in the blood, changes in the brain, something that might get a handle on what's wrong biologically in this particular subtype. And as I said, the work's been really influential. Some of these labels, like seasonal depression, is one I think that's kind of seeped into the public lexicon. Everyone is familiar with the idea that some of us get, especially in New York and Ottawa, probably too, northern latitudes, around the time that the seasons are changing and we're getting exposed to less light. Some people are sensitive to that in terms of their mood. And yet, despite how influential this work has been, the fact remains that there really is no one-to-one correspondence between any of these subtypes and any biological marker that's in widespread use today that I can use for a patient in my office to help make some clinical decision. For the most part, it's still based almost always on my interview of the patient and the history that I'm able to get about the patient. So it would be great if we could come up with more with subtypes that were more rooted in biology. So what we wanted to test in the work I'm about to describe today was whether we could flip that upside down. Let's try to subgroup people based on co-occurring patterns of biological alterations. And then if we can subtype them in that way, let's ask whether those subgroups are predictive of interesting differences in the way their clinical symptoms present, and maybe most importantly, in the way they respond to treatment, so that I can say this treatment is very likely to work for this patient, but it's not likely to work for this other patient, and so in this other patient, we should be thinking about a different treatment. And that was kind of the basic goal. The method that we used, and you're going to be hearing a lot about it today, so I'm just going to take a minute to kind of unpack it for you. It's called resting state functional magnetic resonance imaging. It's a mouthful, but it's actually not that complicated. It's very similar to the kind of brain scan, an MRI brain scan that you might get in a hospital if you had a head injury and they were worried that there might be a bleed in your brain or a tumor in the brain. It's basically giving you a nice image of the brain non-invasively, just in a scanner. And based on a series of seminal discoveries, really, that were made by scientists like Bharat Biswal, Mark Rakel, almost 20 years ago now, they discovered that the brain, those images you see on the left, that at rest, the brain exhibits spontaneous fluctuations in the signal that we're measuring out of the brain scan. And that's what you see happening on the right. You see those spontaneous fluctuations. And it turns out that regions of the brain that are strongly connected to one another fluctuate together. And that kind of makes sense. That's what you see on the upper right. These blue and red lines are going up and down together over time. And that makes sense because, if this region of my brain and this region of my brain are connected, then when this region becomes active, this region is also going to tend to become active. So they're going to tend to go up and down together. And we can use that discovery to look for these correlations, these measurements of how similar these signals are over time. And we can use that to build maps of how strongly people's brains, different networks in their brains are wired. And the analogy I like to think about this with is kind of similar. I flew here today. It's kind of similar to our nation's airport network. Airport networks tend to be organized into hubs. So there are some airports usually located in big cities like Toronto or Chicago O'Hare or LAX. And these airports are connected to many or most other airports in the country. But I grew up in Wisconsin. If I wanted to get somewhere from Wisconsin, I usually had to fly first to Chicago or to Minneapolis in order to get to these hubs. And we've all experienced, anyone who flies regularly has encountered problems where it can be a beautiful sunny day like today, but there's bad weather in Chicago. And because of that bad weather in Chicago, that chaos kind of percolates out throughout the entire network. So dysfunction in these hubs can cause problems throughout the network. And in the same way, the brain may be organized into hubs like this, and dysfunction in particular hubs can cause problems elsewhere. And that's really, in a nutshell, what we're trying to measure here with these brain scans. In order to do this work, I knew we would need a lot of data. And so I went around the country begging people to share their data with me. And the people you see here, I like to highlight them up front because they're the ones who really made this work possible. They were generous enough to share the data that they had collected over many years with me. Some of them shared data before it was even published, which in science, people aren't always willing to do. And so I'm very grateful to these people for making the work possible. Most of the work I'm going to describe comes from this first data set, which, just by way of a little bit of background, was made up of 711 people who 333 of them had unipolar major depression basically, and they were collected from 5 different cities, 5 different scanner sites, and we used this data to discover the subtypes to develop diagnostic biomarkers for diagnosing them in individual subjects. We use machine learning, artificial intelligence type methods to train computers basically to figure out how to diagnose these subtypes. And you may read about these in the paper. I see them like on the front page of the New York Times and the Wall Street Journal every now and then. They're getting a lot of interest for the positive things they can do when they're used well. One of the things that they're kind of notorious for is what we call overfitting to idiosyncrasies in the data they're trained on. So you get a result in this one data set today, and then when I try to replicate that in another data set tomorrow from different people, it doesn't work as well. And so it's really important to design your study in a way to avoid that and to test that you were successful in avoiding it. And that's where this second data set came in. So these are the 2 data sets. I'm going to jump into telling you just about some of the results. I'm not going to dwell in detail on all of the methods, which probably won't be of interest anyway. I'm going to kind of focus on just a couple of the most interesting results. And that way we'll have plenty of time for a conversation and questions at the end. Please, make a mental note of your questions, and I'm happy to talk about anything that I skip over here. So the bird's eye view of the method that we used was first we looked for particular connections in the brain, connections between brain circuits that were altered in depression. And then having identified those, we searched for subgroups of people that showed particular patterns, like subgroup A might have alterations in circuits 1 and 2, whereas subgroup B, circuits 1 and 2 are normal in those people, rather circuits 3 and 4 are altered in the second subgroup. So we just asked, what are the data telling us? We didn't impose any of our own expectations on it. Search for subgroups. Then we developed classifiers, diagnostic biomarkers for identifying them in individual subjects and differentiating them from healthy, not depressed people. And then we tested whether those subtypes could tell us something about the kinds of clinical symptoms that people present with, and which treatments are most likely to be helpful for them. The data we're looking at looks like this. I told you that we can extract like a brain scan time series from each one of these regions of interest, spanning pretty much the whole brain. And you saw this figure before. We ask how each one of these regions is correlated with every other region, and that allows us to construct a big map that looks like this. And it's basically kind of like the airport map I showed you a minute ago. It tells you how strongly each brain region is connected with every other brain region. As you can see, it's complicated, right? There's a lot of little different colored elements in this map, 33,000 unique elements, in fact. The brain's a complicated organ. This is a little technical. If you're interested in how it worked, please ask me at the end, but just suffice it to say that we were able, in this kind of data-driven way, to discover two components, two groups of connectivity alterations in depression, one of which was associated with particular depressive symptoms, anhedonia, like a loss of interest in activities that you used to enjoy, psychomotor slowing, just feeling like I don't have a lot of energy, literally not moving very much, and guilty rumination. And then there was this second component that was not related to anhedonia or psychomotor retardation, but rather was associated with struggling with anxiety and insomnia. And having identified those two components, we could then ask, do all people with depression have high levels of both of them? Or maybe it's the case that some people just have high levels of like one of these alterations, but not the other. Maybe other people have low levels of both. Who knows? We just ask what the data tell us. And that's what you see here. This is the result of what's called a hierarchical clustering analysis. Again, the details aren't as important as much as just being able to see that there are at least 4 groups of people. This is called a dendrogram. It's kind of like a family tree, but instead of grouping people by their blood relatedness, as you would in a family tree, you group them by how similar their brain scans are. And the linkages in this tree have a meaning. The higher the linkage, like this is the highest linkage, the more different are the things being linked. And so what you can kind of see here is that the linkages connecting the clusters, like this one and this one, they're much higher than the average linkage connecting a pair of subjects, people, within a subtype, which tells you that this subtyping is meaningful, that I'm grouping people who are similar, putting them together, and differentiating them from people whose brains look very different. And I'm going to give you a couple of examples of that. So here are like similar to the maps I just showed you, but they're boiled down and simplified now. Now we're just looking at connectivities, features, circuits that are altered in depression and differ in these 4 subtypes. And in these maps, warm colors like red and yellow and orange denote circuits whose connectivity is strengthened in depression compared to not depressed people. Cool colors denote circuits whose connectivity is weakened in depression compared to not depressed people. And the main thing you can appreciate just by glancing at this is that these maps look very different, right? Like over here we have a lot of orange. Over here in these two subtypes we have barely any orange. There are many other differences, but again, all of our eyes are well trained to detect differences in our visual environment, and you can see just by glancing at these maps that they are quite different. Not everyone with depression has the same problems in the brain, and that perhaps makes sense based on what I told you at the beginning about how many different kinds of symptoms people with depression present with. We also found that these subtypes were associated with different kinds of clinical symptoms. So we could talk at length about this, but I'm just going to give you a couple of examples. You see like subtype 2, for example, had very low levels of anxiety. As we know, some people with depression do. Not everyone with depression is anxious. And they also had a lot of fatigue, just feeling physically exhausted, couldn't get out of bed, didn't have the energy to do anything. On the other hand, this subtype 4 had very high levels of anxiety. They also had a lot of difficulty sleeping. They were physically agitated, had difficulties sitting still, and they had a lot of anhedonia, a lot of decreased interest, pleasure in activities that they previously used to enjoy. So these subtypes are associated with very different brain circuit maps, and also they predict differences in clinical symptoms. And that's what we've learned so far. I'm not going to go into detail on this, but I think the main take-home message here is just that using the machine learning methods I referred to earlier, we can take those brain scans and we can use them to diagnose these 4 subtypes of depression in individual patients based just on the brain scan. So I don't have to even see the person or ask the person anything about them. All I need is the brain scan, and I can reliably assign people to these subtypes. The accuracy rates are like 84 to 91% in this data, and a little lower in the replication sample, like 80% up to 90-some percent. I think the accuracy rates aren't as important, and this is one thing I like to emphasize at this point in talks like this. I think that what this tells us is that this approach is promising and probably can be further improved in future with new studies that were designed explicitly to do this. It's not ready for use in the clinic today. We definitely need to replicate it and improve upon it, and there are many other steps involved. But what I think this tells you is that this is a promising approach, and there's hope for achieving better outcomes for patients using methods like this. And in the last few minutes, I'm just going to tell you one reason why we're excited about it, what it might mean for actually delivering different treatments to different people based on the scans. Before I do that, I'll also just because I think this is interesting. It's more of a curiosity, but I think it's quite interesting. So I'll just touch on it briefly. We also found that these depression subtypes, that they cross diagnostic boundaries in interesting ways. So I've shown you so far that our DSM, our diagnostic textbook, assigns people with at least 4 very different connectivity maps for different brain problems to the same diagnosis. And that was interesting, and that led us to ask kind of the converse question, which is whether DSM might assign people with similar brain problems different diagnoses based on kind of superficial differences in the way they happen to be presenting the day they show up in the clinic. The diagnosis that we focused on here is called generalized anxiety disorder. It's quite common. There's a lot of reasons we thought we might look at that one first. Many people with depression also have anxiety. Many anxious kids grow up to be depressed adults. We know that the genetic risk for anxiety, generalized anxiety, and unipolar depression, that they're related. We know that people with depression in their families often have other family members with anxiety and vice versa. So we think there's a lot of reason to believe that these two diagnostic categories might be related in some way. And so we just ask, let's take our diagnostic classifiers, our biomarkers, let's apply them to people who have generalized anxiety disorder but not depression, and let's just see what it shows. And what we found, draw your attention just to this Venn diagram here. One of the findings was that many of the alterations in generalized anxiety disorder in these brain circuits also occurred in depression. They're not overlapping, right? They're different, as we'd expect they should be. Like, many people with depression don't have any problems with anxiety, so they shouldn't be completely overlapping. But about a little more than a fifth of what was altered in all people with generalized anxiety was also altered in depression. So that kind of confirmed our suspicion at the brain level that these are related to some degree. And then when we applied our biomarkers to subtype these people, you might have expected if GAD, generalized anxiety, and depression were completely unrelated, that our biomarkers might tell us that they're all not depressed. But that's not what they told us. What they told us is what you see depicted here. So about 31% of people with this generalized anxiety diagnosis were classified as not depressed. But the remainder, a majority, were classified as belonging to one of our depression subtypes. And interestingly, almost all of those people fell into subtype 1 or subtype 4. And you might remember, I didn't actually present this data to you here in the interest of time, but I told you that some of the subtypes had differences in anxiety. The 2 subtypes that had high levels of anxiety were subtypes 1 and subtypes 4, the same 2 that a lot of people with GAD are being assigned to. Then when you look at their other symptoms, their anxiety symptoms, they don't differ by subtype. They're all high. They're all anxious, and that kind of makes sense. But if you look at their depressive symptoms, they do. The people who tested positive for one of our subtypes had higher levels of depressive symptoms than the people who tested negative. And if we look at a particular item on one of these scales that asks people about how anhedonic they are, how much pleasure or interest they have in activities they used to enjoy. We find that at levels of anhedonia are high in subtypes 3 and 4, which are parallels what we found in the depression-only data set. They also had high levels of anhedonia in subtypes 3 and 4. And importantly, we also wanted to know, you might be thinking, I know I was, okay, that's interesting. It seems like this alternative approach to diagnosing depression and anxiety in individual patients suggests to us that the DSM boundaries are fluid and maybe need some revision, that people who are similar get different diagnoses sometimes and people who are different get the same diagnoses. But there was also a nagging question in my mind, which was is there any specificity here? Are we just catching some kind of brain marker for generalized distress, some like general risk for developing any psychiatric condition in a really non-specific way that might not be clinically useful? So we were worried about that. So we wanted to look at how this would treat people with a different mental illness that we think isn't as related to depression, and that was schizophrenia. And what we found was that schizophrenic patients, almost all of them tested negative. So we do think that these biomarkers are detecting something in the brain that confers risk for becoming depressed or anxious or having some combination of those symptoms, but it does it in a specific way. Lastly, in my last 2 minutes here, I'll tell you a little bit about treatment, which is what I'm most excited about, and I think it's what most patients and their families are most excited about. I know I've had a lot of experience with this, working with patients, how frustrating it is to not know what the right treatment decision is. Oftentimes, we're left, we can make educated guesses based on some information we can obtain from our patients, but for the most part, we do a lot of trial and error in psychiatry, and many of our drugs take a while to take effect, and so that means that some people might have to undergo a 6 or 8 week trial of an antidepressant only to discover at the end of it that I'm still just as depressed as I was at the beginning, and I need to start over and try a new drug, and of course that's really disappointing, and it's not the way we'd like to be doing medicine if we had alternatives. And so one way you might imagine improving on that, one would be developing fundamentally new treatments, and we're interested in that too. But what can we do soon? And another thing you might imagine doing is taking existing treatments and trying to predict which individual patients are most likely to benefit from them today. We know that our treatments, they are effective. They're just not effective for everyone. And if only we knew who those effective people and not effective people were, we could maybe make better decisions. And so the treatment we looked at in collaboration with Jonathan Downer, a friend and colleague at the University of Toronto, was repetitive transcranial magnetic stimulation. You may not have heard of this treatment. It's a magnet-based brain stimulation treatment. You wouldn't know it by looking at this fancy image here where you see the person's brain, but this is a non-invasive treatment. It's delivered through the scalp in an office. It doesn't require any anesthesia. You just go in, you're in and out in 30 minutes. And we know this treatment works. It's cleared by the FDA for depression. And we also know this is a map that tells you the distribution of the circuits that were most specific to one or more of our subtypes. In other words, you can think of this map as a map of brain areas that differ strongly between the subtypes. And one of them, it's labeled DMPFC here, dorsomedial prefrontal cortex. The label isn't as important as just the point that this area, which was very different in the 4 subtypes, is also a target, a therapeutic target for this treatment. So we just asked, okay, if these subtypes have very different dorsomedial prefrontal cortexes, it might stand to reason that people who get this treatment targeting this brain region might respond differently to it. And that's indeed what we found. We found that if you had subtype 1, you were highly likely to respond well to this treatment. If you had subtypes 2 or 4, you were highly unlikely to respond well to this treatment. It just probably wouldn't do much for you. And if you had subtype 3, the odds were kind of intermediate. It might work or it might not work. And we could actually use that information take the same machine learning approach, train computer algorithms basically to make predictions in individual patients. And we were able to predict on an individual patient basis in this pre-existing sample who would go on to respond to TMS and who wouldn't with pretty high accuracy. So we're excited about that. Again, it's not ready for use in the clinic today or tomorrow. We need to replicate the result. And maybe equally importantly, we'd really like to not just predict who's going to respond to this treatment and who won't, but rather address the question of differential treatment prediction. If I'm considering treatment A and treatment B for a person sitting in my office, can I tell them which one of those two treatments is most likely to work for them, rather than just delivering the kind of disappointing news that treatment A is not going to work and I don't know anything about treatment B. So that's something we'd like to do going forward as well. We're excited about this work. There's a lot of work still to be done, but I think the main message is that we and many others in this field are moving forward, and I think there's a lot of hope for achieving better outcomes in psychiatry, and not just in depression, but probably in other conditions too, in hopefully the not too distant future. Before I take questions, I just want to highlight again the folks in red who were kind enough to share their data with me. A lot of the work, the analysis itself, was done by a very talented graduate student named Andrew Drysdale, who's now a psychiatry resident at the University of Washington. I also want to acknowledge my sources of financial support. I have no financial conflicts of interest to disclose. These are all not-for-profit research foundations that are supporting the work that we do, and I'm very grateful to them too. So do we have a few minutes for questions now? Great.